Okay, so thank you very much, Manuel, and good afternoon to everyone. I would start giving you a very brief presentation of the Geosolving company. I am a geological engineer, and Geosolving is an engineering company based in Torino that mainly provides services and solutions in the geoengineering field. We are, as I said, civil engineers and geologists, and the company was born in 2013 with the name of Resolving, as you can see here, and we are a former spin-off company of the Politecnico di Torino. We are specialized in advanced numerical modeling to solve geological and geotechnical issues, energy geostructure design, and monitoring and the early warning system. Among them, here you can see the GeoAndes system, that is the main topic of this on this webinar, and which I'm going to show you in the next slide, as well as other projects which we are already developed, such the EVUSAR system, that is for automatic processing of displacement and velocity maps obtained from ground-based interferometric synthetic actuator, and the OptiAlp system, which we are currently testing and developing. I think this project is quite interesting and promising, since for OptiAlp we are using distributed optical fibers for the early detection of the occurrence and avalanche and debris flow. But this is another story. So let's start with the description of the of what we are looking at. So with the GeoAndes system. So I'm a geologist, so I'm probably much more familiar with this kind of natural dangerous phenomena. But for clarity, I think that two very short definitions are now required. Debris flow, so debris flow are a particular type of landslide. There are fast-moving landslides made up of a mixture of water, rocks, and debris that are particularly dangerous to life and property because they move quickly, destroy objects in their paths, and often strike without warning. Similar to debris flow, we are dealing with avalanches that are rapid flow snow that is occurring down a slope such as a hill or a mountain, and they are primarily composed of flowing snow and air, but also there they are capable to move, have the capability to capture and move ice, rock, soils, and trees. So the common feature of both these two mass-moving phenomena is the capability, as I said, to move quickly up to 100 kilometers per hour and more, and travel for long distances. So from the point from the point where they originated, which corresponds to the upper portion, as you can see in these pictures, in the upper portion of the mountains, and they move to the top, to the bottom of a valley typically. This characteristic, of course, made these debris flows and avalanches very dangerous for all the elements exposed to the risk. That means people, houses, villages, linear infrastructure, and so on. So they particularly, for instance, debris flow occur as a result of very intense rainfall, which are, as you can probably able to say here, that are more and more frequent in the Alpine. So now, after this brief introduction, let's see the specific site where the GeoAndes system has been applied. So back in 2017, to make this story short, the autonomous region of Valle d'Aosta at first, and then the Cogne municipality asked us to design and for the design and the development of a monitoring and early warning services to mitigate the risk of debris flow and avalanches that are occurring along this access road to the Valnute villages. This road is located at an elevation between 1,050 and 500 meters above the sea level. As you can see as you can see there, and this crossed by two gullies that that are called Buvat Gully and Pontoff gullies, that are very deep and steep current in incision that represent the main output of two sub-basins, as you can see there, that are located on the left flank of the LoRa Development Valley. So to extremely simplify, this means that there's no avalanches or the debris flows could travel along these incisions and travel and reach the bottom of the valley and cross the road in here. You can see in the yellow circles, interrupting at the same time the access to road to Valente. Obviously, as you can imagine, this is extremely dangerous for vehicles and people traveling along the road. Please note that this is the only access to the Valente villages, and these villages, even though is very small, some people live there all over the years, and in winter and summer is a very touristic place, because it is one of the main access to the Gran Paradiso National Park. This means that that a very high risk along the road is present, and so someone needs to do something. So we have developed and installed the GeoAndes system. So at first, here you can see an overview of the system. We were asked to deploy a system for one of the two gullies that is called the Buva Gully. Therefore, after few site inspection, a lot of brainstorming with all our colleagues in 2017, we have designed a specific early warning system based on a single trigger line, as you can see there, two traffic lights placed along the road, two cameras, and one weather station. Each element is equipped with a specific radio nodes in the framework of the creation of a wireless sensor network, and this is provided by Wynette, as Emanuele said. At the beginning, the main issue we need to face is the correct positioning of each element of the network, since we had a lot of constraints. Overall, one of the main constraints that we need to face is the accessibility of the place to install the trigger line along the gully. And this is very challenging, because the places are difficult to reach, and this was overcome by defining a correct distance between this position, this trigger line, and the traffic lights. The invasion areas are another very challenging requirements, because the traffic lights need to position it outside the invasion area, because all the vehicles that stop along the road needs to occupy a safe, obviously a very safe place. Then to overcome this, to overcome the distances and the problem of communication between the different radio nodes, we use the LoRa kit, and this was with this we were able to overcome these problems, and so we were able to deploy and install the early warning system as shown here. Here is it. I'm showing you particular or a detail of the trigger line. This is formed by tilt sensors. These tilt sensors were suspended on ropes, on wire ropes, and there were two cables, one structural cable, one positioning cable, and each of these tilt sensor is linked to a counterweight that is directly suspended above the channel where the snow or the debris occur, and when this is hit by the mass, this made this plate rotates, and so the tilt sensor is able to measure the differences between the vertical position and the effective last position, and by using a specific threshold, it is possible to generate an alarm signal. So this is a detail of the WSN, the wireless sensor network gateway that is the coordinator node that performs the continuous interrogation of the tiltmeters, generates, as I said before, the alarm package for turning on the traffic lights if the alarm threshold is exceeded, and collect and sends all the data to an FTP through a 4G connection. So these are some images, some picture which show the detail of the installation of the WSN coordinator node. These are pictures of the traffic lights which were installed along the road, and this is I want to stress that each traffic light is equipped with two lamps, one red light to indicate the road closure, another yellow light that is flashing to indicate possible danger, and then a further camera has been installed to monitor the road. This picture is a detail of the installation of the electronic boards that are assembled inside the cabinet that you are able to see here. And this is the weather station that is equipped with a pluviometer, a thermometer sensors, and an anemometer. And this is completely powered by batteries and photovoltaic modules. So it's completely standalone from all the other elements of the wireless sensor. So after a few years that we were installed the early warning systems on the Buva Galli, we were asked also to install another system along another galley that is, as I showed you before, is located very close to the first one. So we were asked by the Cogni municipality to develop this early warning system, and this task was a bit more challenging than the previous, since this galley is characterized on average by an higher frequencies of occurrence, both of avalanches and debris flow, and by the fact that the potential invasion areas along what we called the alluvial fan, our geologists would call alluvial fan, this area here is much more larger than the one that is present on the Buva Galli. So therefore we were forced to install two different trigger lines that we call number one and number two, trigger line number two, and to have sufficient time to detect the passage of the mass on the trigger line and stop the traffic before the mass could reach obviously the road. In this case, from the beginning, we already used the LoRa tracer receivers to do this job, because also in this case the distances between among the different nodes are quite larger, so we have to overcome this problem of communication between all the different radio nodes. So in this case, for the trigger line, we used wire sensors. Then I will show you a detail in the next slide. Here you can see the trigger line number one. We installed two different wire sensors across across the channel, and this is a picture of the camera and the control node. So we have obviously a control node and a camera that is able to take pictures every 1 hour or 2 hours. What is the situation along this channel. So this is a detail of the wire sensor that is formed by two switches on-off switches. So the switches they're closed when the wire is tensioning. This is the case of the switch number 1, or when the wire is breaking, and this is the switch number 2. So when this happens, a specific signal is generated, and so the traffic lights are turned on. So now in the next slide, I will show briefly how does the functioning of the system. So when there is no alarm, the system is collecting data. So as I said before, the coordinator node is able to interrogating the for instance, here you can see the BUVA, the situation and the scheme of the BUVA galley. So is interrogating the tiltmeters and all the node, and is able to collect and send data in over internet. And so every maybe 20 or 15 or 20 minutes, the user can see if everything is okay, and obviously the road is open to traffic and no alarm is triggered. Another possibility is to turn on the yellow light flashing. This function is to be used mainly in unclear situation, for instance, during heavy rainfall, snowfalls, and whenever the system does not work properly, so as not to exclude human control. And this means for the vehicles that travel along the road that the road is open, but possible danger is present along the road. So particular caution is required, and a speed limit is envisaged along the road. The last option is during the functioning is when there is the occurrence of the avalanche or the debris flow along the channel. Then in this case the tiltmeters overcoming the threshold. So this is in real time sent by to the collector, to the coordinator node. So the coordinator node generates the alarm. They turn on the traffic lights to turn on the red light, so the traffic is blocked along the road. And then an SMS and email are generated and sent to specific recipient of personnel, which is in charge of the management of the security along the road. For instance, in this case, the technical people of the municipality. So this is, as Emanuele said before, is completely, the system is completely manageable through the GeoAndes app that allows to easily check the monitoring network status, sensor cameras, traffic lights, as well as we can query the graphs showing the measured data. So you can manage all the system through this app. Now, to conclude, I will show you some of the some events that we were able to see, to capture in along these two galleys. The first one is an avalanche occurrence in 2018. So after maybe 3 or 4 months after the first installation of the BUVA early warning system. So you can see the trigger line before the avalanche occurrence, and this is after the avalanche occurrence. So you can see a huge amount of very wet snow that is propagating along the channel. As you can see here, we we have all the counterweights that are linked to the tiltmeters. So this is the mass has hit the counterweight, and the specific thresholds on the tiltmeters were exceeded. So the alarm was sent to the traffic lights. We were lucky because in this case the avalanche, as you can see here, stopped about 30 meters above the road. Here you can see after the generation of the alarm, the personnel of the municipality was promptly informed, and here you can see a vehicle that is going through the road, and someone has arrived to check the situation. The road now is closed, but this is a vehicle of the municipality of Cogni, has checked that the mass has stopped about 30 meters uphill. And this is we were particularly unlucky that year, because after 3 months another great avalanche occurred in April, in the 14th of April, and here you can see in this case a huge amount of snow is coming down and has reached and interrupt completely the road. As you can see in the red circle, you are able to see the position of the traffic lights. And in this case, I want to stress that the position of these two traffic lights was obviously designed in order to not to keep clear the potential area that can be invaded by the snow mass. So this is particularly important because the traffic and the vehicles should be stopped upward, downward, in respect to the crossing of the gully, in order to keep the condition of safety for everyone. The last event that I want to show is a debris flow that is occurred the last years in June. In this case, we are talking about the Pont of Galli. So here you can see it's better to see that you are not able to see no more the road. The road is here. You can see maybe a vehicle that is keeping clear the road from all the debris and the rocks. And here you can see another picture from above the channel. And here, this is the road. So a huge amount of material, a huge amount of debris was channelized in this gully and was deposited on the road. And also in this case, our system, early warning system, was able to turn on the traffic lights and thus stopping the traffic along the road, keeping condition of safety all around, during all the events. So to conclude, what are the critical aspects for the creation of an effective early warning system? This is, you can interpret as a take-home message. So it's really important a correct design of the early warning system, because if the design is not accurate, is very, very difficult and to create an effective early warning system. Another aspect that is important is redundancy, because in general, all the early warning systems should be redundant. Then obviously you have to select the most performing radio components. For instance, in this case, the LoRa kit that we use, and that, as I said before, has allowed us to transmit all the signal correctly and continuously between the different node sensor. Another aspect that is important is the data interpretation. So this means, we can automate, we can, as I can say, the human contribution for the early warning system is still required, because we can keep keep some particular processes in an automatic way, but then we need to interpret all the data that are collected. And then the last point is the management, the maintenance of the early warning system, because without maintenance, we can install at first the early warning system, but then we can obviously maintain it in a good state, because early warning system should assure a continuous functioning during all the time, 24/7 and 7 day by 7. So thank you, and I just finished my presentation. So